Dear viewers, in this lecture, let us learn about the deriving the influence line diagram for indeterminate beams. To begin with, let us start ILD for a propped cantilever beam. So this is a propped cantilever beam. The support A is fixed. We have prop or support at B, RB. RB is the reaction at the propped end. So to obtain the ILD for reaction at the propped end. So the reaction at the propped end is the important factor, because once RB is found, we can use this RB to obtain shear force at any section. Similarly, to obtain bending moment at any section, this RB will be playing a vital role. So to derive this ILD for RB, we will be using Muller-Breslau's principle. So the Muller-Breslau's principle is nothing but when we want to derive ILD for any property, say for RB, remove that property and apply a unit load in its place. The resulting deflection curve due to this unit load to some scale will represent the ILD for that property, that is ILD for RB. This is Muller-Breslau principle. Remove the property for which ILD is required, apply unit load in its place, the resulting deflection curve to some scale will represent the ILD for RB. So then say this will be the deflected shape. This is the deflection at XX, YX, and this is the deflection at B, YB. So this ILD ordinate for RB is given by this YX divided by YB. So this is what we meant here, to some scale. So this will give the scale required for the ILD, YX by YB, and this we got by using Betti-Maxwell's theorem. So now we need to get YX as well, YB. So YX is the deflection at XX and YB is the deflection at B. So to find YX and YB, so let us take section at XX. So the distance is X. So bending moment at XX will be equal to this load 1 multiplied by X. So this will be, we need to use the sign convention. So our load is to the right side, unit load is to the right side, and that unit load will produce an anti-clockwise moment. Therefore, right anti-clockwise plus, therefore plus 1 into X. Force is 1 and distance is X, produces anti-clockwise moment, and it is to the right side of the section. Therefore, plus 1 into X. We have EI d squared by dx equal to minus mxx. There is a general second order differential equation for fluxural problems. So we need to substitute minus mxx. So mxx is x, therefore minus mx will be minus x. This is equation 1. We are going to do a double integration. That is, integrating once this equation, will be getting EI dy by dx equal to minus x, when integrated will be getting x squared by 2 plus c1. This is equation 2. Now integrating this equation 2 with respect to x, will be getting EI y equal to minus x cube by 6 plus c1 x plus c2. Now we need to find these constants of integration. So using the boundary conditions. So if you see the boundary condition, say this is the deflected shape and we are measuring x from the right end. So here at the right end, we will be having some deflection, similarly some slope will be there. Whereas at the fixed end, the slope as well the deflection will be 0. So how do we write the boundary condition? Say here x is 0 here. So when x takes a value of L, deflection is 0 as well, slope is 0. So that is written like this: when x equal to L, dy by dx equal to 0. That means slope is 0. When x equal to L, y equal to 0. That means deflection is 0 at this fixed end. Now we are going to make use of these two boundary conditions. So this we call as the slope boundary condition. This we call as the deflection boundary condition. Now using this boundary condition in this equation 2, put dy by dx equal to 0, x equal to L, therefore minus L squared by 2 plus C1, therefore we'll be getting C1 equal to L squared by 2. Then using the second boundary condition in this equation, in the deflection equation, put y equal to 0, x equal to L, therefore 0 equal to minus L cube by 6 plus C1x. C1 we have already found as L squared by 2, L squared by 2 into L will be L cube by 3, or L cube by 2. C1 is L squared by 2, so L cube by 2 plus C2. Therefore, we'll be getting C2 as minus L cube by 3. Now, substituting the values of C1 and C2 in the general equation, we'll be getting general equation for slope and deflection like this: EI dy by dx equal to minus x squared by 2 plus L squared by 2. That is plus C1. C1 is L squared by 2. Then general equation for deflection is EAY equal to minus x cube by 6 plus L square by 2x minus L cube by 3, C1x plus C2. So we'll be getting Yx, font Yx, this will be equal to 1 by EA into this. Then to find Yb, that is Yb is the deflection at B, we need to put x equal to 0 because Yb means deflection at the property end. So where x equal to 0, therefore we'll be getting Yb equal to minus L cube by 3A. Therefore, if you put Yx by Yb, that is minus EA will get cancelled on both sides and both terms. So we'll be getting minus x cube by 6 plus L squared by x minus L cube by 3 divided by this minus L cube by 3, or we need to multiply every term by the reciprocal. So minus x cube by 6 into 3 by minus L cube plus L square by 2x into 3 by minus L cube minus L cube by 3 into 3 by minus L cube. So this will result in x cube by 2 L cube minus 3 by 2 x by L plus 1. Then let us use a term that putting x equal to NL. The meaning of this is x is the distance from the right end to the fixed support. So at any intermediate point, it will be fraction of L. So that fraction we are putting as using the term small n. So putting x equal to NL. So put x equal to NL here. So n cube L cube divided by 2L cube minus 3 by 2 NL by L plus 1, because this will become 1. Therefore, if you simplify, you'll be getting ILD ordinate for RB as n cube minus 3n plus 2 by 2. This is the ILD equation for RB, that is reaction at the property end of a propped cantilever beam. Now we will do a small numerical example on this. That is, we need to construct ILD for RB of a propped cantilever of span 8 meters. Compute ILD ordinate at 1 meter intervals. So draw the propped cantilever beam. Divide into 8 equal parts because we need 1 meter intervals, therefore 8 equal parts. So 8 equal parts can be divided like this. So if we have a length, make a center, then divide this into 2, similarly divide this into 2, similarly in between. So we'll be getting 8 equal parts like this. You can easily do this. So number them. So let us start with 0, 1, 2, 3, 4, 5, 6, 7, 8. We need to proceed from here because we always measure x from the property end. So the ILD ordinate equation for RB is given by n cube minus 3n plus 2 by 2. This we have derived earlier. Now we are going to apply here and get the ILD for RB. So we need to draw a tabular column like this. Point x distance in meters, n equal to x by L. How we got this? Because we have put x equal to NL. When we want n equal to x divided by L, that is this a fraction of L. N value is fraction of the L. So ILD ordinate for RB. Now point 0. At point 0, x takes a value of 0. Therefore, n will become 0. Substituting the n value here, we will be getting 1.000. Then at point 1, x takes a value of 1 meter. N takes a value of 1 by L. L is 8 meters. So 1 by 8 is 0.125. Substituting this 0.125 here, we will be getting this value. Then at point 2, x equal to 2. N equal to 2 by 8. X point 3, x equal to 3. Then 3 by 8. 4, 4 by 8. 5, 5 by 8, 6, 6 by 8, 7, 7 by 8, 8 by 8. Substituting all these n values in the equation, we'll be getting the ordinates, ILD ordinates for RB. So ILD ordinates will be 1 at the property end and it reduces. So 1.813, 0.633, etc. And we need to connect these with the help of a curve because this is a third order equation. Therefore, this need to be connected with a curve. So this is the ILD for RB. And here the Muller-Breslau principle gets satisfied. That is ILD, we want to draw ILD for RB. So we have removed RB and apply unit load in its place. The resulting deflection curve to some scale will be the ILD for RB. So dear viewers, thank you all for your constant support in subscribing our channel.